Friends, today we shall study about the synchronous machine representation for stability studies. In this we will study the simplified model with amortizers neglected and a constant flux linkage model. Now, here before I discuss the simplified models, let us see the per unit system of equations which we have developed so far. I will just summarize the per unit system of equations which we have developed for the synchronous machine. These three equations, that is these represents the stator circuit equations in dq of frame, and all these terms are expressed in per unit. All the currents, flux linkages, the voltages are expressed in per unit. The time is also expressed in per unit. The second set of equations are the per unit rotor voltage equations. Now, here while writing the per unit rotor voltage equations, I have considered one amortizer on d axis and two amortizers on the q axis. The field winding circuit voltage equation is EFD equal to P psi FD plus RFD IFD. Similarly, the equations are written for amortizers, right. 0 equal to P psi 1D, R1D, I1D. Now, here I put this subscript 1 to indicate that this is the there is one amortizer on the d axis, or amortizer number 1 on the d axis, right. If there is a 2, then it becomes second winding also on d axis. Okay. 0 equal to P psi 1D, psi 1 q plus R 1 q I 1 d, and similarly the last equations. Then in these equations which were written, we need the expressions for stator flux linkages. Therefore, another set of equations are the stator per unit stator flux linkage equations, per unit stator flux linkage equations. These are written as psi d equal to minus LAD plus LL ID, LAD IFD plus LAD I1D. Now, here if you see here, this LAD is the mutual inductance between stator and field winding. Okay. Now, in the per unit system of representation, we have made all mutual inductances on the d axis equal. So, that you will find that this LAD appears here. Similarly, this term, when this term represents the mutual inductance between direct axis amortizer and d axis of the stator winding, right. Therefore, again this comes out to be same. Similarly, for quadrature axis windings, we have flux linkage psi q equal to minus LAQ plus LL IQ plus LAQ I1Q plus LAQ I1 I2Q. Okay. Again these are all mutual inductance are made all equal. The last equation is the flux linkage due to the zero sequence currents. Then we have equations for rotor flux linkage equations, which are expressed in per unit rotor flux linkage equations. Okay. Now, again if you see here, again we find actually that in the rotor circuit also we get these terms LAD, LAD. Okay. Now, we have to see the last equation is this per unit air gap torque, T is equal to psi d I q minus psi q I d. This is the per unit torque in the synchronous generator. Now, this is the complete set of equations for representing a synchronous machine. Okay. And if you want to study the dynamics of the synchronous machine, then this set of equations plus the swing equation have to be solved, and we have seen that these equations are nonlinear differential equations. Okay. And these equations can be solved by applying numerical technique. Now, in case actually the system is small, right, then we can easily solve these equations and obtain the complete solution. But when we talk about the power system stability problem, where we may come across hundreds of generators, thousands of buses, a realistic power system which we have today, even in our country, right, has large number of generators and large number of buses. Therefore, the dimension of the system is very large, and for analyzing the stability of the system, right, if we use this detailed model which we have developed, while developing this model we have not done any approximations, no simplifications were made. Further, I will just emphasize that in these equations which we have written, right, the all inductances are the saturated values of these inductances. That is, you account for the magnetic saturation also while computing the inductances. Okay. Now, if you want to use these equations for stability studies, it becomes very difficult, because the system becomes very large, and for large system the number of equations become very large. Therefore, when we look in terms of simplifying the system model, we always look from the point of view of reducing the dimension of the model, that is, we want to reduce the number of differential equations. Second is that we would like to have numerical technique which can be used to solve these equations quickly, that is the fast numerical techniques and low order model of the system. Okay. These are the main thrust. Looking from that point of view, we shall be studying actually today that how we can make some approximations, simplifications. Now, what we will do is that we will consider some various degrees of approximations, okay, that can be made to simplify the model, minimizing the data requirement and the computational effort. Many times we have a problem also that certain data which are required to use the model are not available. One example is that normally the synchronous machine data related to the amortizers are not easily available, right, and therefore, we have to see that what approximation can be made, so that computations can be fast or computational efforts are reduced, as well as the data which are not available, right, can be or we can do the studies without using those data or getting some approximate data. Now, while looking at these simplifications, the first simplification which has been looked into is that we neglect these P psi d and P psi q terms in the stator circuit equations. This is the first simplification. Now, let us see what is the justification for making this simplification or neglecting the P psi d and P psi q terms. These terms are the transformer voltages. Okay. Earlier I talked about these equations and mentioned that these transformer voltage terms are smaller as compared to the speed voltage terms, right. But if you see this equation, these stator circuit equations, only because of this transformer voltage terms, these equations are differential equations, right. And if we neglect this transformer voltage term or the derivative terms, right, then the stator voltage equations become algebraic equations. In fact, these terms represent the stator circuit tangents. Okay. Now, I will just discuss what is the justification for neglecting these terms. Now, the stator circuit is connected to the transmission network, right. Now, so far the transmission side or say the transmission network transients are concerned. Okay. There is a transmission network transients. The time constants of these transients is generally very low, and whenever some transient phenomena occurs in transmission system, it quickly dies. Time constant is very small, right. And therefore, for system stability studies, we ignore the transmission system transients. We assume that the transmission system is in steady state. We consider only the sinusoidally varying voltages and currents in the transmission system. Although, whenever disturbances occur in the system, like say fault, you will find actually that when the fault occurs, it will have decaying DC components of the fault current. It will have high frequency currents which are also existing in the during the fault system. Okay. And but because of the low time constants, we always ignore the transmission network transients. Okay. Now, if we ignore the transmission network transients, can we consider the stator transients, because they are part of the same circuit. Therefore, if you consider the stator transients, it becomes inconsistent, and therefore, for all system stability studies, this assumption is made. Then the question arises whether this assumption is a realistic assumption, whether the results which we will get by ignoring these terms will be acceptable. People have done a lot of research on this, and after performing detailed studies, the conclusions drawn are that yes, we can ignore these terms, that is the stator circuit tangents can be neglected. I will suggest you to look into the discussion given by P. Kundur in his book on power system stability and control. Power system stability and control. In this, he has discussed the results reported in some research papers and compared the dynamic performance of the system, including the stator circuit tangents and excluding the stator circuit tangents, and compared. Okay. And once you read this, you will come to a very important inference that yes, for stability studies one can one can comfortably neglect the stator circuit tangents, right. And therefore, the moment you neglect the stator circuit tangent, we get very big simplification that the stator circuit voltage equations become algebraic equations, right. That is E d equal to minus psi q omega r minus R A I d, E q equal to psi d omega r minus R A R q, and E o equal to p psi o minus R A. Okay. They are becoming the algebraic equations. Okay. The another important assumption which is made or approximation which is made is, in this equation this rotor speed omega r is assumed to be equal to synchronous speed. That is, in per unit system we make omega r equal to 1, right. This is another assumption. Now, in practice, by making this omega r equal to 1, there is not much simplification in the system model. However, the very interesting thing which is there is that if you assume omega r equal to 1, then this assumption to some extent counterbalances this assumption, that is where you neglect the stator circuit tangents. That is, if you analyze the system performance neglecting only p psi d term, p psi q term, p psi o term, okay. Second time you do the studies neglecting both these terms, right. Then the not neglecting both the terms, sorry, by making the second assumption, correction, that is we are neglecting this transformer voltage terms or stator circuit tangents and assuming this rotor speed to be equal to the synchronous speed, right. If we make both these assumptions, right, then the results which we get are more closer to the actual results, right. And therefore, this assumption is also a very desired assumption. Now, in the same book, Condor in his example 5.1, in example 5.1, he has established considering small perturbations that effect of neglecting the speed variation counterbalances the effect of neglecting the stator circuit tangents. I will suggest that you should carefully study this example 5.1. Okay. Now, these are the two major assumptions which have been made. Now, with these assumptions, let us say develop the model, a simplified model which we will get after. Okay. That is, if you make this assumption, then the equations will become like this. For a balanced three phase system, E d will become equal to minus psi q with omega r is 1 minus I d r a, E q equal to psi d minus I q r a. That is, these are the two stator circuit equations which we shall be using for further system studies, and no more simplifications are done so far the stator circuit equations are concerned. Now, with these simplifications we can derive the expression for the electrical power output and electromagnetic torque or air gap torque. You can see that the power output P t is E d I d plus E q I q. Now, substitute the expressions for E d and E q from these equations. Okay. These algebraic equations, you substitute this. With this substitution, you will find actually that the terminal power P t will come out to be equal to psi d I q minus psi q I d. Okay, psi d I q minus psi q I d. This is the expression, minus R a times I d square plus I q square. This term can be identified as stator circuit loss or stator circuit resistance loss. Therefore, we say that terminal power is equal to the air gap torque minus armature loss of the stator. That is why I said that when you have to calculate actually the torque Te, right, or air gap power, we first calculate the terminal power, we know it. To that we add the armature resistance drop, I am sorry, armature resistance loss, not drop. And this is a very important equation which we shall be using. Okay. Now, after making these two major simplifications, we can make some further simplifications. That is, if you look into the model, in the stator circuit equations become the algebraic equations, okay. But when you look at the rotor circuit equations, then the rotor circuit equations are differential equations. Okay. Now, next set of simplifications which can be made are that we neglect the amortizers. We have amortizers located on the rotor. Okay. Now, here I would like to just caution you that many times people have considered the amortizers in the mathematical model, right, but we can make some simplification here by neglecting the amortizers. Now, the justification for neglecting amortizers are like this. One is that the synchronous machine parameters related to amortizers or synchronous machine parameters related to amortizers are generally not available or not easily available. Okay. This is one, and therefore, if the data is not available, we have to take some approximate data and use it. This is one. Second is that these tangents associated with the amortizers are also fast tangents. Their time constants are also low and generally they decay fast. Therefore, the moment you neglect the amortizers in the system or amortizers on the rotor circuit, what we gain? What do we gain? Just can you tell me? Just tell me what do you gain actually by this? Because I had mentioned that these are the four equations related to the voltage related to the rotor circuits. Okay. This is the equation related to the field voltage, the field circuit, sorry, this is related to the field circuit, this is related to the amortizer on the d axis, and these are the two related to the amortizers on the q axis. Now, if I neglect these amortizers, then these three equations disappear, and these are the three differential equations. Okay. And therefore, the immediate advantage which I get is the model becomes of lower order. Number of differential equations which I have to write down for the system will reduce. This is one advantage which I get immediately, that is the model order gets reduced. And you can easily understand that if the number of differential equations are less, right, then the solution becomes faster. The second advantage which we will get here is that while performing the simulation studies or dynamic simulation studies, we can use higher or the larger time step for integration, because the time step which we use for integration of the differential equations, it depends upon the time constants of the system, right. And in case you want to capture the complete dynamics of the system, right, our time steps should be small enough to take care of all the time constants. In case the moment we neglect these 3 differential equations, we get very important advantage, and that advantage is that the remaining equations have larger time constant, and we can use larger time step for simulation. And once you use larger time step, then our computational efforts are reduced. Therefore, we get 2 major advantages, both one in terms of reduction in the order of the system, second is reduction in the computational time or simulation time by using higher or larger value of time step for integration. Okay. Now, with this 2 assumptions which we have made here, the stator circuit equations are now algebraic equations. Okay. The rotor circuit, the equations related to amortizers we have neglected. Then we are left only with one differential equation, that is EFD equal to P psi FD plus RFD IFD. This equation is corresponding to the field circuit of the synchronous generator. Now, this can be written in this form, P psi FD equal to EFD minus IFD RFD. It is a differential equation, we write down the derivative term on the side, and therefore, one has to note down very carefully that this is the only differential equation associated with the electrical characteristic of the machine, right. The swing equation are always there, right. Therefore, whenever you study the dynamics of the system, we have to consider the differential equations associated with the synchronous machine, stator and rotor circuits. But after the simplifications, we find that we have only one differential equations which is associated with the electrical characteristic of the system, and therefore, my model becomes very much simplified. Now here I will just present how an alternative form of machine equations. So far the equations which we have written, right, these equations were written in terms of the field current, okay, and flux linkages. Now, another form of equations, the only change in the form, actually there is nothing new, is that we define the terms like this. Here we define the term E I, there is slight mistake here. E I, a voltage proportional to I F D, that is E I equal to L A D I F D, a voltage proportional to I F D, that is field current, right. Field current is I F D, and a term when you multiply this by L A D, mutual inductance, right, then all these things are all expressed in per unit quantity, right. Therefore, this E I term is proportional to I F D, because this L A D becomes a proportionality constant. Therefore, this is one term which we define here. Second term which we define here is a voltage E Q prime, which is proportional to the field flux linkage, that is psi F D. That is, instead of talking about the field flux linkages, we talk about a voltage term, and this voltage term is proportional to this flux linkages, and this is the proportionality constant. And the third term which we define is E F D. Now, this E F D is the voltage applied to the field circuit, right. We transform this by multiplying with a multiplying factor, again these are per unit quantities, right. Therefore, this is a constant, and E F D a voltage term proportional to the field voltage. Okay. That means instead of calling this term EFD, I will now express in terms of this term EFD, which is related to this voltage by this multiplying term, there is a coefficient. Okay. Now, when I use this, when I use these terms now, or the newly defined terms, and use our equations, okay, the equations which we have got are, they are the basic equations. Therefore, let us write down the equation for psi d. Okay. The equation for psi d can be written now after making all the simplifications here. Psi d equal to minus L d I d plus E I. You can just look into the simplified equations which we have developed. I will just show you again. Anyway, okay. Similarly, you can write down another equation for EQ prime using the previous equations, that is equation number 12.9. Okay. You multiply this both sides by LAD and divided by LFFD, you will get an equation in the form EQ prime equal to minus LAD square divided by LFFD ID into EI. This term, which is the coefficient of ID, has been identified as difference of the direct axis inductance minus direct axis tangent inductance. In fact, this I shall establish in my next lecture, that is LD minus LD prime comes out to be equal to LAD square upon LFFD. This derivation is to be done separately. Now, if you make this substitution in the equation 12.12, we will get the result in the form, that is EQ prime is equal to EI minus LD prime ID. Right. Now, here this ID is normally, this is small ID, not capital ID. We use this direct axis component of the stator current. Okay. Similarly, you can use this equation 12.10 to obtain an equation of the form, that is P EQ prime equal to 1 upon TDO prime EFD minus EI. Now, here I think I will just show that equation. If you take this equation, this is the equation, we had P psi FD equal to EFD minus IFD RFD. Okay. You multiply both sides of this equation by LAD over LFFD. Okay. When you multiply both sides, you will have the term here P multiplied by LAD divided by LFFD into psi FD, and this term is identified as EQ prime as per our new definition. Okay. Similarly, this EFD, when it is multiplied by LAD upon LFFD, you multiply both sides by RFD and divide by RFD. That is, you multiply and divide this term by this term RFD. So that what happens is that we can identify this term as 1 upon TDO prime. This is called the open circuit field time constant. Open circuit field time constant, because what is this LFFD? It is the, this is the inductance of the field circuit, and RFD is the resistance. Therefore, the L by R is the time constant. Okay? And this time constant term is a very important term for our stability studies. This time constant term is generally of the order of 5 to 10 seconds. Okay. Therefore, this is the equation now which is put in the form P Eq prime equal to 1 upon TDO prime EFD minus EI. That is the equation which we have earlier, which was in this form, differential equation P psi FD equal to EFD minus IFD RFD. This has been transformed in terms of the newly defined variables. That is, EFD is the voltage proportional to field voltage, EI is the voltage proportional to field current, and EQ prime is the voltage proportional to flux linkages, field flux linkages. Okay. Therefore, now you have in this equation you find that we have only voltage terms, not the current or flux linkage term. This is only difference. Now, I am here summarizing the model of the synchronous machine, which is most commonly used for system stability studies. That is, we write down psi d, the flux linkage of the d axis, equal to minus L d I d plus E I. Okay. Psi q is equal to minus L q I q. E q prime, the expression for E q prime is E I minus L d minus L d prime I d, and P E q prime dot, that is the d by dt of E q prime, is equal to 1 upon T d O prime E f d minus E I. Therefore, in these 4 equations, what we see here is that these 3 are the algebraic equations and 1 is the differential equation. Therefore, the synchronous machine is very commonly represented by these equations, only one differential equation. And what this differential equation is, if you look at it very carefully, this differential equation is related to the field circuit of the synchronous generator. It is a field circuit. We started with this was the equation, EFD equal to P psi FD plus RFD IFD. This is the equation for the field rotor field circuit. Okay. And this has been transformed in this particular form, and the terms like EI is related to ID, LD like this. Similarly, EQ prime, which is in this equation, is related by other terms. Okay. Therefore, these are the interrelated terms. This is the differential equation, but these algebraic equations are also required to be solved along with the differential equation. Okay. Now, next very important thing is that we can draw a Phasor diagram under tangent conditions. Sometimes we even feels actually that how can we draw a Phasor diagram under tangent conditions. But since we have neglected the stator circuit transients, and therefore, so far the stator circuits are concerned, it carries the balanced 3 phase sinusoidally varying currents, right, and therefore, you can represent or you can draw a Phasor diagram under tangent conditions. Now, to draw the Phasor diagram, we again start with our basic model. That is the original equations. We start with the original equations. Oh, there is a lot of papers here. We start with these equations because we had developed these equations. Okay, ED equal to minus psi q minus RA into ID or ID into RA. Okay. Similarly, EQ equal to psi d minus IA IQ into RA. Okay. Therefore, we will make use of these equations to develop a Phasor diagram. Now, let us take this term EQ equal to psi d minus RA IQ, RA IQ, mistake here. Okay. Now, this psi d term, this is the flux linkage term, can be replaced by psi d can be replaced by minus L d I d plus E I, and in per unit system the inductance is equal to the reactance, that is L d can be written as X d per unit system, right, because X d is nothing but omega into L d and omega is 1. Therefore, I can write down this equation now, E q is equal to minus X d I d plus X A d I F d minus R A I d, that is this term is identified as E I, and therefore, now I can write an equation, very interesting equation for E I. Can see this started with E q, this is the fundamental stator circuit voltage equation, okay, or stator circuit equation. Now, in this equation we are substituting the expression for psi d, which we have already developed, and we are also replacing this L d terms or L E d terms by X d or X A d terms, because in per unit system they are same, the reactance is the same as the inductance per unit. You get the equation in the form E I equal to E q plus X d I d plus R A I q. This is one very important equation. What we do is that this is actually the algebraic equation, that these are all magnitudes of these quantities. This can be transformed into Phasor equation. What we do is we multiply both the sides by j. You multiply both the sides by j, then you will get j times E I prime, E I equal to j times E q, j times X d I d plus j times R A I q. You have not done anything except that this equation is multiplied by j all through. Once you multiply this by j, then this term j E I can be identified as a phasor, right. Therefore, I can represent this as E I tilde. What will be the location of this phasor? It is going to be along the quadrature axis, because there is a term j associated with it. J times E q, again it is located along the quadrature axis. Then here in this term j times X d I d, I put j X d I d tilde. Now, this j is not replaced because I d is a reference. Therefore, I d when it is a reference, I can call this as a I d phasor straight away. Okay. Since it is a reference, there is no, but in the case of E q, j E q is the phasor, because it lies along the q axis. Similarly, like this, right. Therefore, I get an equation in this form. Now, when you see this equation here, you will find actually that this is E q, which is along the q axis. This term is also along the q axis, that is I d when it is multiplied by j times X d comes across the q axis. This is anyway along the q axis. Therefore, this term E I, which we defined as voltage proportional to field current, is lying along the q axis. Okay. Then we make use of this equation E q prime. Okay. Now, in this equation we have E q prime equal to E I minus L d minus X d prime into I d. Okay. Here we replace this E I by this term E q plus X d I d plus R A I q. After this replacement and replacing X d, L d and L d prime by X d and X d prime, we will get the equation of E q prime in the phasor form, E q prime in phasor form as E q prime equal to E q plus j times X d prime I d plus R A I q. That is this, again these three terms you can see here, they are this sum is lying along the q axis. That is this E q prime also lies along the q axis, E I also lies along the q axis, Okay. Then earlier we had defined one term EQ, that is the voltage behind this impedance Ra plus j times xq, that is terminal voltage. To this terminal voltage we added this term, that is Ra plus j times xq into IT. This term also came out to be along the q axis. Okay. Therefore, this EQ in the Phasor form is represented as EI minus j times xd minus xq id. That is, we can express this EQ which was defined earlier as a voltage behind this impedance. Okay. This is also along the q axis, and we have seen actually that it is this voltage phasor which defined the location of q axis with respect to the terminal voltage. Therefore, whenever we start drawing the Phasor diagram, the first requirement is that we have to establish the location of D and q axis with respect to the terminal voltage. And now we have established a relationship between this EQ and EI. Okay. Now, this can be written in this final form. This term define, not D-line, define. We can define one more term here. Now, let us see what this, can you just interpret this equation? For example, I had the equation in this form, EQ equal to ET plus RA plus J times XQ into IT. Okay. Therefore, we have another term which we divide as E prime equal to ET plus J times ET plus this impedance into IT. This impedance is RA plus J times XD prime, subtangent direct axis reactance. Okay. It means this is the voltage behind this impedance, terminal voltage plus voltage drop in this impedance. This voltage is, and this voltage is, can be simplified and expressed in the form, you just make the substitutions, right. ET can be written as ED plus J times EQ, IT can be written as ID plus J times IQ, and therefore, this E prime can be written as ED plus RA ID plus J times XD prime IQ plus EQ plus J times XD prime ID plus RA IQ. Is this whole thing will come, that is, substitute the value of ED EQ from the expressions for ED and EQ which we have already developed, that is the previous expressions, I think. Okay. Now, here one thing which we observe is that if you take this voltage term, okay, then this has two components. One will be along the D axis, another will be along the Q axis. The Q axis component of this quantity comes out to be EQ prime. The EQ prime which we defined as a voltage proportional to field flux linkages, right, and the q axis component of E prime comes out to be a quantity EQ prime, right, and therefore, now I have drawn a simple Phasor diagram to represent all these quantities. This is not a very unknown Phasor diagram to you, right, but to make these things complete, what we do is that you start with terminal voltage V ET. Okay. Let us say this is the terminal current. Now, this and the phase difference between terminal voltage and terminal current is always known to you. Then to this ET we add this voltage drop RAIT plus J times XQ IT, RAIT plus J times XQ IT, you will get this term EQ, and this EQ will define the position of Q axis. Once this q axis is defined, you resolve the terminal voltage into two components, E t as E q and E d. Similarly, the terminal current can be resolved into two components, I q and I d, right. Then in this phasor diagram, we can show this term E prime, a voltage behind direct axis tangent reactance. That is, what you do is that you take E t, to this you add R a I t plus j times x t prime I t. Therefore, this is the location of E prime, and the when you resolve this E prime into two components, the q axis component of E prime is E q prime, right. Therefore, most of the relations which we have derived can be easily remembered with the help of this phasor diagram. Okay. Now, any doubt, I will suggest that you start with our basic equations and make these simplifications step by step, okay, and establish the new equations or equations in terms of new variables. Once they are established in terms of new variables, right, you can express these variables as phasors, that is E I as a phasor, E q prime as a phasor and E q as a phasor, right. And then also the term which we defined is E prime, this is a phasor. Then the whole everything is expressed in the form of a simple phasor diagram. Okay. Now, let me summarize what we have studied today. We started with the complete model of the synchronous machine. Then we have made these simplifications, we have discussed the simplifications. Simplifications discussed are that the stator circuit tangents are ignored. Another simplification we have considered is the omega r is assumed to be constant. Then third simplification which we have incorporated is we have neglected the amortiguer circuits. With this, the resulting model of the synchronous machine to describe the electrical characteristic has one differential equation, and that differential equation is ultimately written in terms of the variables which we have defined in terms of E q prime, in terms of E I and E f d. Okay. And this model is very commonly used, although we do make some further simplification to obtain a classical model, right, but this is the model which is very commonly used, and any simplification beyond this will not give you the desired results, although it will give you the information, right, but sometimes you can get approximate information about the stability and then go for detailed information. Okay. With this I conclude my today's presentation. Thank you very much.